All right, so once you figured out which one's stronger, you can assign them roles in this reaction. Then you can predict the products, right? The conjugate acid and the conjugate base. And then finally, once you got both sides of your chemical equation, you can draw in those electron pushing arrows. All right, so we have this acronym, ARIO, that we use to sort of keep in mind to compare acid strength here. So first of all, which one of these is going to play the role of the acid? The molecule on the left or the molecule on the right? Anybody got it? Okay, let's think. ARIO, the A stands for what? Atom, the atom holding that negative charge. So in this case, when we're comparing acid strength, we're really going to look at our conjugate bases. So I'm going to remove these hydrogens, replace them with a lone pair. Okay? And we're asking ourselves, which one of these is more stable? We go to that A in ARIO, right? The more electronegative an atom is, the more stable it is holding that negative charge. So then which one of these is going to be the more stable conjugate base? The one on the left or the one on the right? The one on the right, right? Because oxygen is more electronegative than nitrogen. So our stronger acid is going to be the molecule on the right. This is our acid. That means that this one is our base in our acid-base reaction. Okay? So remember, when we're talking about acid strength, we're really talking about how stable that conjugate base is. Now that I have my acid and my base assigned, I can do my products by drawing my conjugate acid. So I'm going to take my base, and I'm going to add a proton in place of that lone pair. Right, that will have the effect of increasing that charge by 1. Again, this is my conjugate acid. And then I'm going to draw in my my conjugate base. That's going to be my acid, but now deprotonated, where that oxygen is replaced by a lone pair. I'm sorry, that hydrogen is replaced by a lone pair, and the charge decreased by 1. And now that I have my sides of my chemical equation, I can play my spot the difference game and draw in my electron pushing arrows. There is a new bond that forms between your nitrogen and the hydrogen on my acid. Oops. So I'm going to draw that bond formation arrow. And then I have to break that existing hydrogen-oxygen bond using another electron pushing arrow. So again, we got two different molecules. We're mixing up these two different molecules here. Once we determine which one is the stronger acid, that's the one that's going to play the role of the acid in our reaction. The other one will be our base. Then we can go ahead and draw on our products. We know how to do these conjugate pairs. And then we can sort of tie it all together, button it up by doing our electron pushing arrows. Okay? Cool. So the A of our REO, and both of these molecules do have resonance as well, but that's they're the same for both of them. They both have those resonance structures available. So here's our base, here's our acid, right? As we said last time, the stronger acid, that's going to be the acid in the reaction. The weaker acid is going to be the base. So now that we have our acid and our base determined, we can do our conjugate pairs. My conjugate acid is when I take my base and add a hydrogen. So now I'm going to replace this lone pair on my nitrogen with a new bond, nitrogen-hydrogen bond, and increase that formal charge. That's my conjugate acid. And my conjugate base is when I take my acid molecule and I remove a proton, I remove a hydrogen, and replace it with a lone pair and decrease that charge by 1, right? So again, our lone pair in our base became a new bonding pair of electrons. Likewise, our old bond in our acid became a new lone pair. All right, and so the last thing that we can do to finish it off is to put in those electron pushing arrows for this reaction. So everybody take a second and put in those electron pushing arrows. That would give us our product. I'm going to need to draw one bond formation arrow for my new bond. So I'm going to start at the lone pair on the nitrogen, connect it to that hydrogen atom where that new bond is being formed. All right, and then am I done? I'm going to need one more. So you're always going to have two arrows for these acid-base reactions. One bond formation, but then we also need to break that existing oxygen-hydrogen bond in my acid. Okay, cool. One more thing that I sort of thought about after the fact here, but everybody take a second and rank these from strongest to weakest, or I guess weakest to strongest acid. All right, and remember when I'm talking about acid strength, I'm really talking about what? What should we really be thinking about? The conjugate base, right? The stability of the conjugate base. So it might be even more helpful if we take these and draw the conjugate base for each of these. Okay? So to be clear, if we want to look up here, how am I getting my conjugate base? Remember, I'm going to take my acid here, I'm going to remove a hydrogen and replace it with a lone pair, and then I got to decrease that charge by 1. All right, that's how we go from our acid to our conjugate base. That's how we're able to predict our products in these reactions. So I'm going to do that for each of them. Remove a hydrogen, replace it with a lone pair, and decrease my charge by 1. Remove a hydrogen, replace it with a lone pair, and decrease my charge by 1. All right, so these are my acids. These are my conjugate bases. Okay, and when we want to know what is the strongest acid, we want to know which one of our conjugate bases is the most stable. All right, so A, B, C, which one of these conjugate bases is going to be the most stable? B, why B? What's up? Because it's stable, yes. That's circular logic though, right? What is it about B that makes it more stable? It's neutral. It's got 0 formal charge. A has a formal charge of -1, and C has the absolutely, you will never see it in your life, formal charge of -2 sitting on that nitrogen. All right? So if we're going to arrange these from strongest to weakest, our strongest is this middle one here, and the weakest is this one here. Okay? Now, this one did not fall under that ARIO rule here. So we're going to make a new one here. F for formal charge. All right? Because we know atoms are most stable with a formal charge of 0. Okay. I spent way too much time thinking about where in our acronym this should go, because remember our ARIO acronym here, we sort of had arranged from the part that had the most influence on stability to the least influence. All right, and formal charge is definitely very important. I was debating either AFRIO or FARIO. And although it doesn't sound as cool, I think FARIO is going to be the one here. So formal charge is super important, right? So our acronym here is FARIO, not to be confused with his little brother Mario. Had a lot of success in plumbing, all right? Cool. And remember, the whole shtick about this acronym here was it allowed us to qualitatively compare acids, right? We have 2 similar acids up here, and we're able to, just by looking at the structure, determine which one is the stronger of the 2. Okay? But sometimes that's much harder of a judgment call to make, right? So let's say that we wanted to compare something like HCl and sulfuric acid, which is this structure here. Okay, H2SO4, all right? If we wanted to compare these 2 acids here, okay, yes, chlorine is a better atom for holding that negative charge. I guess let's go ahead and look at our conjugate bases here. All right? Chlorine is large and electronegative, but oxygen's pretty freaking electronegative too, and in sulfuric acid here, my conjugate base has a whole lot of resonance associated with it, right? Multiple resonance structures. Now we got like a bit of a difficult situation. One is better in the A, the other one is like really good, 3 different resonance contributors stabilized in the R here. So how do we sort of make this, how do we tease this apart? Which one's the stronger acid? So for these, you can't really apply those qualitative rules. They're just not similar enough. But we have a grandmaster cheat sheet for comparing acid strength here, what is called a pKa table. Okay? So this is from an appendix. This is actually a different book. I just like this table more. It's got more information on there. But this compares the pKa values of a bunch of different acids. Okay? And we can determine which is the stronger acid based on these numerical values here. We can numerically compare these things. All right? So let's make sure we know how to use this. So first of all, let me just remind y'all, you would have learned in Chem 1B about the acid dissociation constant Ka. And this would be the equilibrium constant between, say, if we're just going to stick with our HCl here, reacting hydrochloric acid and water to produce hydronium and the conjugate base, the chloride ion. Okay, Ka is that equilibrium constant that governs that reaction, right? How far does this reaction proceed towards the products? Does it favor the products or favor the reactants, right? And you will have learned how to use these Ka values to determine the pH of a weak acid. They were really important for that, okay? So then the pKa is just the negative log of that Ka value, right? So I don't know your life. Typically, you had these Ka values listed in a table, and you looked them up for these weak acids when you needed to use them. We basically have the same thing, just now the negative log of all those values on our pKa table here, right? So for each acid that's listed, we have a numerical value for its pKa. Now, good news, we're not going to do any math. We're not going to do any equilibrium ice table business like you did in Chem 1B, okay? But we need to be able to compare these two. And if you remember, the larger the value of Ka, the more that reaction favored the product side, right, of this here, so the stronger the acid. Well, so if we then take the negative log, it's sort of the opposite trend that we see for pKa. For pKa, the larger the value, the weaker the acid. Right? And likewise, a small value indicates a strong acid. Okay? So we were trying to compare HCl and sulfuric acid, H2SO4. So we're going to go to our table. We're going to look them up. Okay, everybody take a second. Part of what this is good, okay, and I'll show you where to find this table here, but part of it is going to be just the fun of hunting through it to find what you need, right? And the first time you look through it, it's going to be like, oh my gosh, what's going on here? And then you sort of get a sense of where everything is, and it's not too bad. Notice that these are sort of represented in that condensed structural formula. Remember, we talked about how that was important to be able to read those condensed structural formulas. We see that our molecules here are listed in these condensed structural formulas. Okay, so I'll give you a hint. We're over here in this first column. Can anybody find our HCl for me? -7. All right, and what about that sulfuric acid? The -5. Okay, so here's our pKa values. Oops. -7 for HCl, -5 for sulfuric acid. So which one is the stronger of the two acids? HCl, right? The one with the smaller pKa value. Okay? And again, this constants page here is posted to Canvas, and this is what you'll need to use for your homework. Okay? I'll show you where that is here at the end where you can find that. All right. Cool. So we can now we have this like numerical sort of cheat sheet for all these different acids we can look up. I guess just to point out here how this table's organized, it's organized from the absolute strongest acid, the one with the lowest pKa, and then at the absolute other end of the table is our weakest acid with a huge pKa. Okay, so the stronger acids are at the front of our table here. Okay. The other thing that I just want to point out about this table that's kind of nice and you can use to sort of help you study here is if we just kind of zoom in here, right, and we look at these here, we can now use these pKa values to kind of illustrate these things that we learned in our ARIO, or now our FARIO acronym, right? The only difference between these three acids here are the inductive effect of those halogens. Fluorine is the strongest inductor because it's the most electronegative, followed by fluorine and then bromine, and we still see that illustrated with these pKa values as well, right? That we can see that sort of here. So it's a good idea to just kind of look through here, and you can compare similar things in order to sort of have this numerical value now associated with acid strength that illustrates those concepts that we were learning qualitatively previously. Okay, all right. So we will wrap all this together here in a second, but the one thing that we've kind of neglected talking about up until this point is base strength, right? We talked a whole lot about how to compare different acids and figure out which one was the stronger acid. Now let's talk about base strength. Okay? Okay, so just to review, for acids, we said that the stronger acid had the more stable conjugate base. All right, so we looked at those conjugate base molecules and we compared their stability, and that's how we were able to determine acid strength. Because what made an acid a really good acid was that after it got rid of that proton, it was cool. It was all happy, all by itself. It didn't need that hydrogen to begin with, right? So what we're going to see is the opposite for bases. Okay? If we're talking about base strength, the stronger base is the less stable. Right? What makes it unstable? It's super mad that it doesn't have that hydrogen on it. So it's going to grab a hydrogen from anywhere it can. Okay? So we're going to play that same game here. If we look at two different bases, which one of these is going to be the stronger base? The one on the left or the one on the right? Why the one on the right? Because it's less stable with its formal charge. Nitrogen's furious here. It doesn't want to have that formal charge of -1, so it's going to grab a hydrogen from anywhere it can get it in order to not be so unstable. Okay? So we can use those same sort of qualitative principles here, but now we have this little cheat sheet, this pKa table. So how could we possibly use this to compare base strength? Okay, well, there's this inverse relationship between acid strength and base strength, right? And we said that. We said that the stronger the acid was, the more stable the conjugate base was. The more stable the base, the weaker it is, right? So a strong acid has a really weak conjugate base and vice versa, right? So strong base implies a weak conjugate acid. All right, so let's try to do this. We're going to compare two bases. We're going to first do this qualitatively, right? Just using those principles, and then we're going to look at the table and double check our work here, okay? All right, so let's look at our acronym. Formal charges. Can I use formal charges to differentiate which one's stronger? No, they're both carrying that same -1 formal charge. What about the atom carrying the negative charge? Is this going to differentiate these two? No. And then what about resonance? So one of these structures does have resonance and the other one doesn't, right? So which one has resonance? Let's make sure that we can see this. Right. The one on the right, okay? So then which one of these is our stronger base? The least stable of the two, right? The one that needs that proton, that negative charge plugged up the most, right? So this would be the more stable, which is why it is the weaker base. Right? And again, we used resonance to determine this. This is the stronger base because it's less stable. What's up?
I originally thought that the right one would be the less stable because of the oxygen atom, and it so oxygen is kind of like electronegative, right? So it kind of wants, that entire structure kind of wants the nitrogen in a way, but is it because this one's less stable?
So this lone pair can come down here, and that negative charge can spread itself out between both the oxygen and the nitrogen, right? So remember, more resonance, more spread out charge is more stable. Okay, so now we need to be able to use that pKa table as well to compare these base strengths, right? So I'm going to look up on my pKa table here, but this isn't a list of bases, right? So what am I going to look up for each of these molecules? The conjugate acid, right? So I'm going to have to look up the conjugate acid for each of these. So everybody take a second. Let's practice. Let's make sure we can go back and forth here. Draw me the structure for the conjugate acid of each of these molecules. Okay, so again, sort of just to see it visually here, I'm going to replace one of these lone pairs with a new nitrogen-hydrogen bond. And what's going to happen to the charge? It's got to go up by 1. So this will go from -1 to 0. So same thing over here. Erase a lone pair, replace it with a new nitrogen-hydrogen bond, and increase that charge by 1. So these are the two compounds that I'm going to be looking up here. Okay? I'm kind of realizing I shot myself in the foot a little bit. We're going to have to approximate our ethylamine with methylamine here. This has one fewer carbon, but it's going to be about the same. So we're going to call this one 40. Okay, then I'm going to give you a second to find this other one on our chart here. Oops. Kind of zoom in to get you in the right direction. Does anybody see it? Where is it? 16. Excellent. This one right here. All right, so this conjugate acid is 40. This conjugate acid has a pKa of 16. Okay, so which one is the stronger acid? Right, the lower number, the stronger acid. And remember, the stronger the acid, the weaker the conjugate base. So indeed, we get the same result. Our stronger acid, this is our weaker base. So this one would be our stronger base. All right, so comparing base strength here. Which one is the stronger base? What are we going to do? We're going to look up the pKa of the conjugate acid. Right, the weaker acid, or weaker conjugate acid. That gives us our stronger base. And the weaker the conjugate acid, that means what? A big pKa or a small pKa? Big pKa. So the weaker the conjugate acid, aka the larger the pKa, the stronger the base. All right, so now we're going to roll all this together here. Everything that we've done up until this point, maximally understand these acid-base equations here, okay? So we're going to start with sort of where we've started before. I'm going to put down two molecules. You're going to determine which one's the acid and the base and complete that chemical equation. All right, so step one was to determine the acid and base. Remember, the stronger acid is our acid. The weaker acid will play the role of the base. Okay, Step 2, we got to draw those products. Those conjugate pairs. So let's do step 1 here. Which one of these is going to be the acid? The one on the left or the one on the right? The one on the left, right? Because if we look at our acronym, it wins in both atom and resonance, right? The one on the left will definitely produce the more stable conjugate base. So this is our acid, and this is our base. Okay. Likewise, we can convince ourselves even further if we look up the pKa's. This one we just looked up was 40. For the sake of practice of looking crap up on a table here, everybody take a second and see if you can't find me the other one. Anybody got it? What is it? 4.8. This one right here is the condensed structure for our acid here. All right, so our pKa here is 4.8. And does that check out? Which one's the acid and which one's the base? Right? The smaller the pKa, the stronger the acid. So check, check. Numbers work out. Okay? So now we're going to draw our products, our conjugate pairs here. My conjugate acid, I'm going to take my base. And I'm going to replace my lone pair with a new hydrogen bond. All right, remember, because that's what bases do. They accept protons. And I got to increase that charge by 1. So again, this is my conjugate acid. And then I'm going to do my conjugate base by taking my acid molecule. And since acids donate protons, I'm going to remove this hydrogen and replace it with a lone pair, decreasing the charge by 1. Right? So this is now my conjugate base. What other fun stuff can we do here? We can put in our electron pushing arrows. All right, so remember, what do bases do? Do they donate or do they accept? Accept. So you're always going to have an arrow from your base reaching out and grabbing that hydrogen, right? Forming that new bond with that proton. And what do acids do? They donate, so you're going to have your acid breaking its bond. Okay? And then the last thing that we can do here is to determine the direction of equilibrium in this reaction. All right, that's the last thing we need to learn how to do with our acid-base reactions, right? So what we're going to learn how to do right now is figure out, does this reaction indeed proceed towards the product side, or does this reaction actually favor the reactant side? Remember, in Chem 1B, you learned how to look at reactions in both directions here, okay? In order to do this, well, all right, we have two acid-base reactions, one in the forward direction, one in the reverse direction. In the reverse direction, it's my conjugate acid playing the role of the acid, and the conjugate base playing the role of the base, right? So I have one acid in the forward direction and one acid in the reverse direction. And what we're going to do is compare how strong those two acids are. All right, the stronger acid is the one that's going to drive the reaction in the other direction. So in order to determine the direction of equilibrium, we're going to look up the pKa of our acid. And then we're going to look up the pKa of our conjugate acid. And we're going to compare them. Okay, so we already did it for our acid. That was that 4.8. Now we need to look up the pKa of this thing here, of our conjugate acid. All right, so I'm going to put up that pKa chart again. Let's get rid of this little marking down here. Okay, everybody take a second and see, oh, whoop, that's not it. Does anybody see it? All right, I'll give you a second. The 10.7, right? CH3 NH3 with that plus there. So now we got the pKa of our conjugate acid. Let me make a little bit more room. Is 10.7. Okay, so again, we're going to compare our acid at 4.8 with our conjugate acid at 10.7. Which one is the stronger of the two? Our acid or our conjugate acid? The acid. So the acid is going to drive the reaction in the other direction. So this is indeed a reaction that will proceed in this forward direction here. Okay? So we look up the pKa of our acid, look up the pKa of our conjugate acid. This reaction will point towards the weaker acid. All right, the stronger acid drives it towards the weaker acid. Okay, so this is indeed a reaction that can favor the product side. All right, we're going to go one step further here, and that is to determine whether or not it strongly favors the products or just weakly favors the products. So when we're talking about equilibrium constants, we say that if an equilibrium constant is within this range of 10 to the negative 3 to 10 to the 3, this is what we call the dynamic equilibrium range. meaning that you can kind of tune your reaction conditions to push it one direction or the other. Doesn't strongly favor one side or the other too crazy. Okay? So if we translate this into our pKa space here, okay, for a pKa, oh, not just the pKa actually, we're going to have to look at the difference between the pKa's of our two acids. So the difference between the pKa's here we're going to define as the pKa of our conjugate acid minus the pKa of our acid okay, and if this delta pKa is greater than 3, this is a reaction that strongly favors the products. A reaction that we would say basically goes to completion. You mix these two things together, it's going to give you just 99.9999, basically 100% of product in this mixture here. Okay? If your pKa is between 0 and 3, this weakly favors the products. All right? Yes, your products are produced. The equilibrium does lie in favor of the products, but there is still an appreciable amount of reactant left behind unconsumed. Right? This reaction doesn't go to completion. Okay? On the other end here, let me actually use dots so we don't get confused. If it's between -3 and 0, this then weakly favors the reactants. Right? So there is a little bit of product produced, but nothing too crazy. This equilibrium does lie in favor of the reactants. And then anything less than -3, this strongly favors the reactants. Meaning you combine those two things together and absolutely frickin' nothing happens. All right? There is no product that's formed. Okay? So lastly here, let's take a second again. pKa, you're doing the product minus reactant, or the conjugate acid minus the acid. So if we go here, let's see if we can classify this. Our acid was 4.8, and our base was 10.7. So what would we say about this reaction here? What's the difference? 5.9? Yeah. 5.9, so that would be a reaction that strongly favors the products. You mix these two things together, you're going to have none of that reactant left over, right? This reaction pushes all the way to the product side there. Okay? So, these problems here, I like these problems because they roll together just about everything we've learned up until this point. Drawing bond line structures, reading condensed structures, electron pushing arrows, acids, comparing acid strength, drawing the products, and then finally looking up these values on the pKa table to determine where your equilibrium lies. Okay? But you definitely have some of these in your homework as well, and just FYI, when I say that I like a problem, that's a pretty good indication that it's definitely going to be on an exam, right? Okay, so anyways, just make sure to give those types of problems a good practice, again, because I like them, but also because, again, they roll together so much of what we've studied. So they're great practice just on a whole bunch of stuff, all right? So let's try to do this from scratch here. How much time we got? Okay. Here we're specifically talking about these hydrogens on my carbon at the end. All right, and let's look up these two compounds real quick. Actually, take a second and give me the molecular formula of these. These polyatomic acids are written on that table just as their molecular formulas. Right, you may recognize this polyatomic ion here, but anyways, take a second and get the molecular formula for this. How many H's, how many C's, how many O's? Anybody got it? All right, so that structure would be for H2CO3, carbonic acid. Okay, so 6.4. So let's just mark that one down. Okay. And then this one's going to be definitely weaker, but let's just grab this value to convince ourselves. Okay, you need the condensed structure of that molecule, right? So take a second, see if you can do the condensed structure. You see it up there? Yeah, the CH3C triple bond N. This thing right here. Okay, definitely the weaker of the two acids. Right, again, just as evidence of our pKa, 6.4 is a much smaller number than 25. Right, so again, now you're going to draw the products of this reaction. Those conjugate pairs.
For the triple bond on the left side, does that mean there's like two carbons, one at the short end and then?
Absolutely. So
Okay.
if I'm going to draw my carbons here, there's one here and one here. Right? There's got to be one on the other end of that triple bond, and it's just implied.
Okay.
Yeah. right, so for my conjugate acid, I need to take my base and replace the lone pair with a new hydrogen bond. Increase that charge by 1. For my acid, and it doesn't matter which side you pick. You pick the one closest. We're going to do the opposite. We're going to get rid of a hydrogen and replace it with a lone pair and decrease the charge by 1. Okay. All right, so I'm going to put up this pKa table, and you're going to finish off this whole thing. It's still missing its electron pushing arrows, and we need to determine the direction of the equilibrium in this reaction here. All right, do we see our conjugate acid up there anywhere? Very first one, boom. Negative 10.1. All right, and I got a lot of pKa's up here. Which ones am I going to compare? The conjugate acid and the acid. And in particular, I'm going to take that conjugate acid, negative 10.1, and subtract my acid pKa, giving me negative 16.5. So what would we say about this reaction? So it strongly favors the reactant side, right? This is a ridiculously low delta pKa here. This would strongly favor the reactants. And again, practically what does that mean? It means if you mix carbonic acid with this guy here, methane nitrile, not a damn thing's going to happen, right? There's going to be absolutely no reaction that occurs between these two. This equilibrium lies very strongly in favor of the other direction. Okay? So then lastly, just to sort of the one other missing step here were those electron pushing arrows. Again, your base is accepting a proton. So I have an arrow starting at my base, going and reaching out and grabbing that proton. And my acid is donating that proton, so it's going to give it up. So it's going to break that hydrogen-oxygen bond, and that pair of electrons will go on that oxygen. Okay? So again, these sort of problems here, rolling together so much of what we learned how to do. We can determine our acid and base in our reaction, right, by comparing which one is stronger. We can draw our products, those conjugate pairs. If you're having trouble drawing your products, you want to go back to the beginning of this week when we talked about those conjugate pairs. All right? Then you can put in those electron pushing arrows and then finally determine the direction of the equilibrium by looking up the pKa of the acid and the conjugate acid and comparing. Right? The stronger acid is going to push the equilibrium in the other direction. Cool.